Okay, let's get this going. Section 7.5 is graphing systems of inequalities, so you will need graph paper and a straight edge to do these notes. Okay. To solve a system of inequalities, you will need to find all possible solutions. So there's going to be more than one solution for these. And since there are an infinite number of solutions, this can only be done by graphing. So let's back up and do a little review of graphing a linear inequality. First, we're going to graph the equation, in other words, treat it like it's an equal sign, to find the boundary line. Then determine if the boundary line should be dotted or solid. Remember, we use dotted when it's greater than or less than. We use solid if it has the equality beneath it. Pick a point on one side to test back in the inequality, and then shade the appropriate side of the boundary line. So we did that back in the last chapter. So we need to use these same tools to graph a system. Remember, a system means that we have more than one inequality. Okay, so here's an example. This is a system of inequalities, and we want to know what numbers or ordered pairs will fill both of these inequalities. So let's start with the first one. Y is less than negative x plus 1. It's already an mx plus b form, so I'm going to use the y-intercept of 1, a slope of negative 1, down 1 and to the right 1. And remember, we can count that the opposite direction as well. So less than means a dotted line. And I'm going to try and line it up pretty good here. Okay, so we're going to use this dotted line. And then I have to figure out my shading. So I'm going to test 0, 0. 0 is less than negative 0 plus 1. So that means 0 is less than 1, which is false. No, I'm sorry, that's true. So I'm going to shade it down. Now I'm going to be careful because I'm going to put a couple of shadings on top of each other. If you want to color code this, that's great. But what I like to do is just shade a little bit in the direction that I want to go, rather than shading the whole half plane until I get the other line in place. Okay, my other line is y is less than or equal to 2x plus 3. So up 3 from my y-intercept, a slope of 2, up 2 to the right 1, or down 2 and to the left 1. This is going to be a solid line. And again, I'm going to test the point 0, 0. 0 is less than or equal to 2 times 0 plus 3. So 0 is less than or equal to 3. That's also true. I told you could color code this, so let's maybe do that. So this is going to go this way. And then what I'm looking to shade is the areas that are solutions to both systems. So this area up here, the first area, only is a solution to the second equation. This area up here, neither equation is shaded in this area, so that's a solution for neither one. Area 3 is a solution for the first equation, where the red is going, and area 4 is the area that both are shaded, so this is the area we're going to finally shade for our solution. It's really important that you watch your shading and that I can tell where the final shaded solution is. Let me back up a minute and show you the way not to do it. You don't have to do any of this, just leave it the way you did. So if you did your first line, and let's say I'm using all red, I don't have colored pencils, and after you do the dotting here, if you shade this whole area, and then you have your second line, and you know you're supposed to shade this whole area, it's hard for me to tell where you think the solution is. The solution is only this area down here where they overlap. So be really careful, and that's why I say that instead of shading the whole thing, when you get your first line, shade a little bit, When you get your second line, shade a little bit, and then figure out where both areas overlap and then shade that area as your solution area. Sometimes you'll be asked to do 3 lines, and again, this is all just examples. Don't worry about getting any of this stuff down. But if you had a 3rd line in there, let's say we had a 3rd line this way, and if the first line you had shaded really big, the second line you had shaded really big, and then the 3rd line you shaded really big, I can't tell where your solution is. So again, small shading until you know exactly where your area of overlap is, and that should be your final graph for this example. Now the second example is a little different, so don't skip over this one. So x minus y is less than -1. The first thing I'm going to do is subtract x from both sides so that I can put this into y equals mx plus b. Then I'm going to divide everything by -1, and don't forget you've got to flip that inequality then. We'll do the same thing with this one. Subtract the x, divide by -1, and now I have inequalities ready for graphing. So equation number 1 is up 1 with a slope of +1, and it's a dotted line, and I will label that equation 1. And testing 0, 0, 0 is greater than 1 is false, so I'm going to shade this above, and again just a little shading until I get my other line in place. My second equation starts at -3 and has a slope of +1. This is a solid line. These are parallel lines because their slopes are the same. They both have a slope of 1. Let's test 0, 0 here as well. 0 is less than or equal to -3. That's false, so again I'm going to shade away from 0. And the overlap area doesn't exist. There is this whole area up top that is a solution to the first equation. This area down here is a solution to the second equation, but there is no solution for the system. There is no xy ordered pair that can make both of these statements true. So no solution is my final answer. Okay, the last one is a word problem. We're going to look at this and see how it goes. Okay, a farmer has at most 16 days to plant his crops. He can plant corn at a rate of 250 acres per day and soybeans at a rate of 175 acres per day. He has at most 3,500 acres available. How many days should he spend planting each type of crop? So I need a variable for the days spent with corn and a variable for the days spent on soybeans. So one of my axes is going to be for corn, and one of my axes is going to be for soybeans. Now, do you know why I didn't put my axes in the middle of the grid? Since I'm talking about a real-world problem and the amount of corn can only be positive, the amount of soybeans can only be positive, I only need the first quadrant. Okay, days. At most 16 days. So the days that I plant corn plus the days that I plant soybeans has to be less than or equal to 16. So I'm going to use x and y, well, c and s intercepts. The value of c when s is 0 is 16. I'm going to go by 2's. 2, 4, 6, 8, 10, 12, 14, 16. And the amount of soy when c is 0, so let me do this. C when s is 0 is 16. S when c is 0 is also 16. 2, 4, 6, 8, 10, 12, 14, 16. Less than or equal to, I have up to and including 16 days. So there's my first line, and less than 0 is going to be this way. So I can plant any combination of these days. I could plant 4 days for soybeans and 6 days for corn. I could plant 2, 4, 6, 8, 10 days for soybeans and 4 days for corn. I cannot use any combination of days up in this area because that would be greater than the sum of 16. Okay, so that's my days. I also then have some information about total acres. Okay, so corn is a rate of 250 acres per day. So if I plant corn for a certain number of days, say 4 days or 5 days, to find the number of acres, I would multiply by the acres per day. So 250 times the days that I plant corn gives me the acres of corn, plus 175 times the days that I plant soybeans gives me how many acres of soybeans I've got, and this has to be less than or equal to 3,500 acres. All right, so again, let's put in 0 for C. Okay, if where did I do this? I didn't do this on my paper. Okay, so if I put in 0 corn, then 175 S has to equal 3,500, and S equals, let me do this real quick, 3,500 divided by 175 is 20. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's the y-intercept for soybeans. Now I know that I can't plant 20 days because it has to fulfill both parts of the system, but remember I'm doing this boundary line. So that's if the corn is 0, I can plant up to 20 days. If the soybeans are 0, then 3,500 divided by 250 gives me corn has to be less than or equal to 14 days. So even though I have a total of 16 days, because of my limitation on acres, I can't plant corn for more than 14 days. All right, I'm going to connect those two, and again this would be shaded below. So my final shading is going to be this area that looks like this, because everything below both of those lines is my system. Now keep this graph near you. I'm going to go to a new slide and I want to do a little more work on this. So let's see. C plus S equals 16. That's my boundary line. And 250 C plus 175 S equals 3,500. That's my other boundary line. What I want to do is find out the exact point of intersection. Oops, sorry. Come on. The exact point of intersection for this graph. So I'm going to do that using substitution. So C equals 16 minus S. I'm going to plug that in over here. Using a calculator and distributing, I get 4,000 minus 250S plus 175S equals 3,500. Combining my like terms and subtracting 4,000. Negative 75S equals negative 500. S equals 6.6 repeating. Taking that back over here, C equals 16 minus 6.66 repeating, so C equals 9.33 repeating. So when the corn is 9 1/3 days and the soybeans are planted for 6 2/3 days, notice that that does total up to a total of 16 days. I will have the optimum, oops, let's go back, sorry. I will have the optimum amount. So we said 2, 4, 6 and 2/3 for soybeans. 2, 4, 6 and 2/3, and 2, 4, 6, 8 and 9. So my graph's off a little bit, but that would be my optimum crossing point. Okay, so that's how we do it with a word problem, and that's it for the video.